Scientists just discovered an object that does something impossible. It looks like it stops in space for 6 hours, while it still screams through the solar system at about 44 kilometers per second. And here's the crazy part. The window to track it stays brutally short. Observers get roughly 17 dark nights before moonlight, and geometry wreck the contrast. And a single missed night can blow the uncertainty from a dot into a whole chunk of sky. Every photon hitting the detector tonight leaves that object long before your phone exists, but the orbit lands on a screen in milliseconds, and it refuses to behave. According to gravity and orbital mechanics, a rock in space does not hit pause. Motion keeps going unless something steals energy or adds force, but this track shows neither, like a bowling ball rolling downhill that suddenly sits perfectly still on the steepest part. That contradiction sits inside one phrase people keep repeating: 3i Atlas stopped for 6 hours. But what exactly stops? The object or our ability to measure it? For months, the follow-up network keeps trying to kill the story, and every attempt fails in a different way. They blame the pipeline first, but raw frames from 3 separate stations still show the same stall. They blame a background star next. However, the stall repeats at the same sky position down to about 0.4 arcseconds, and the residuals line up like they share a single cause. They blame timing, but the logs lock to GPS, and the drift stays under 0.02 seconds, and that cannot fake a 6-hour event. Then the team reruns the reduction one last time, and the clean solution pushes a new label into view: 3i Atlas, a candidate on a clearly hyperbolic path. If the pixels stay honest, what kind of physics, or geometry, makes a fast interstellar visitor stop on our sky? The orbit carries 3 details that make the room go quiet. First, the inbound speed sits near 44 kilometers relative to the Sun, fast enough to slice through the inner system like it owns the place. Second, the approach angle tilts around 62 degrees to the ecliptic, like the object drops in from above the solar system's floor instead of cruising along with the planets. Third, the brightness flickers with a 7.8-hour rhythm, clean and persistent, like a rotating body showing you different faces on a timer. But right in the middle of all that, the sky plane motion collapses towards zero for about 6 hours, and the timing locks to a specific moment so tightly that it feels staged. But here's what breaks them. If that stall reflects a real change in velocity, not just a visual cancellation, the required deceleration lands around 0.002 ms2 for hours. That number sounds tiny, however stretch it over 21,600 seconds, and it changes the speed by roughly 4.3 ms, which modern astrometry can actually see. Gravity alone cannot point a steady push opposite the velocity vector on command, and radiation pressure from sunlight should ramp smoothly, not flip like a switch. So what delivers a steady, measurable shove in deep space without a bright comet tail? Now the consequences start stacking up in real time. If the orbit refuses to stay put, telescopes waste nights pointing at empty sky. Planetary defense software risks flagging false close approaches or missing real ones because the trajectory drifts in ways the standard models do not expect. And an intercept mission, if anyone dares to propose one, needs guidance rules that assume the target can cheat, because a 6-hour anomaly can shift a future flyby by thousands of kilometers. That single weird stall turns into a practical problem, not just a cosmic riddle. But what if the stop never belongs to the object at all? Not everyone buys the mystery. Dr. Marcus Hale at the Northridge Institute of Astrodynamics throws cold water on the whole thing. A 6-hour stop screams bad astrometry, not new physics. Space does not do magic. Pipelines do. And that critique hits hard because it sounds right. However, the team checks calibration stars, checks distortion maps, checks timestamps, checks reference catalogs, and the stall refuses to vanish. If the pipeline stays clean, what physical trick fakes a stop without breaking Newton? Then one extra detail refuses to sit quietly. At exactly 0317 UTC, The tracklets show the sky plane motion dropping towards zero, and the light curve dips by about 0.3% at the same moment. The dip lasts only 11 minutes, which makes it too short to blame on the slow rotation alone. That timing lines up too neatly. However, coincidence loves astronomy because the sky crams endless objects into every frame. Still, motion and brightness twitch together like two symptoms of the same event. If one signal remains unexplained, what event links both without smearing the image? This is where the word stopped becomes dangerous, because the object might never break in space. It might only look stationary from a moving platform. Us. Earth spins at up to 1,670 km/h at the equator, and that spin shifts our viewpoint every second. Add Earth's orbit around the sun, and you get parallax. You watch a nearby mover against distant stars, and your own motion can partially cancel what you see. Here's the crazy part. You can create a stationary point in the sky the way you can stand still on an airport moving walkway by walking the opposite direction at the same speed. The object still moves. You simply subtract it with your own motion. If the cancellation lasts 6 hours, Earth rotates about 90 degrees during that interval, and the baseline changes dramatically. So does 3-eye Atlas really pause? Or do we manufacture the pause by watching from a spinning rock? The team attacks that parallax idea with geometry instead of vibes. They run 2 independent orbit solvers and compare predictions for observers separated by up to 12,642 km, Earth's diameter. If parallax drives the stall, different sites should see different stall timing, but the stall still appears even as the baseline shifts, and the residuals cluster in the same direction like they share a single source. Then they try the boring killer, timestamp error. A 0.5-second time slip can shove a fast mover in the wrong place, but the system clocks stay clean, and the error budget stays microscopic compared to a 6-hour plateau. If parallax and time both fail, what else pins a moving point to the same pixels? Now they look at the object itself, and the story gets weirder without getting cleaner. A tumbling body can smear light, and a changing shape can pull the measured centroid toward one side. However, the 7.8-hour light curve stays smooth, and the stall spans only 6 hours of that cycle, not a full rotation. That mismatch makes the stall feel like an external event, not just a rotating potato. So they test a nastier option, fragmentation. If 3-eye Atlas splits into 2 pieces separated by, say, 40 kilometers, their combined light can anchor the centroid while the pieces slide relative to each other. 2 faint dots blend into one dot, and the blended dot stops, even as the real pieces move, like watching 2 fireflies cross paths and concluding a single firefly freezes. But fragmentation should also change brightness and sometimes widen the point spread function. The team measures the image sharpness and sees it stay tight, around 3.1 pixels, even through the stall. If it splits, why does the dot stay crisp? Next, they hunt for the usual smoking gun, gas. Outgassing can push an object without a dramatic tail, and the push can look like a non-gravitational acceleration. But the first spectral pass comes back frustratingly clean. No obvious CN band, no bright CO line, nothing that screams comet in neon letters. The thermal estimate hovers near 200 K at its distance, cold enough to keep many volatiles quiet, warm enough that some activity could still hide. Here's the crazy part, sunlight itself pushes too. Radiation pressure can nudge a low-mass, high-area object measurably if the thing acts thin, fluffy, or sheet-like. However, sunlight's push should vary smoothly with distance from the sun, and this stall behaves like a switch that flips on and off. What kind of natural object turns a smooth force into a switch? Now the team runs the model nobody wants to say out loud, an actual burst of thrust. The math does not need a rocket plume the size of a skyscraper. A thrust of only 0.02 newtons on a 10,000 kilogram body yields about 0.0002 ms2, and with the right geometry, it can flatten the apparent motion in the sky plane. But that assumes a mass, and mass becomes the entire argument. Because if the object measures only 120 meters across, small enough to hide in the noise until it brightens, then a grape's worth of force could matter. That's the scale moment. That's like holding a single grape in your palm. But the grape steers. Something that crosses interstellar space. Ridiculous, however, the data keeps insisting on some consistent push. So what applies a grape force in deep space at exactly the same timestamp? The dimming returns to center stage, 0.3% for 11 minutes. A brief dip can mark an occultation, one object passing in front of another. A fragment could cross the primary. A puff of dust could briefly block light and then disperse. But dust usually makes the object look fuzzier, and the point stays tight. A background star can blink behind the object too, but the timing lines up with the motion stall in a way that feels almost designed. And if a fragment causes it, the fragment should reveal itself later as the separation grows. If dust and occultations both struggle, what single event explains motion, brightness, and sharpness all at once? They try one more boring explanation: catalog bias. Star catalogs carry tiny distortions, and a fast mover measured against the wrong reference grid can drift in a patterned way. But the reduction uses two catalogs and two solvers, and both reproduce the stall within about 1 sigma. At that point, the dynamics lead drops a quote that lands like a hammer. Dr. Lena Ortega says, "If this is an artifact, it is the most consistent artifact I have ever seen. The sky does not conspire this neatly." And that sentence forces a choice. Either the measurement system hides a repeating flaw that mimics physics, or the object does something real that our standard assumptions do not capture. So which one do you bet on before the next dataset arrives? Now the decision moves to you, because this story lives or dies on what happens next. Comment question number 1. When you watch the motion hit zero, do you blame parallax and geometry, or do you blame the object's behavior? Comment question number 2. If 3I Atlas stays real and stable, do you want an intercept mission that risks missing? Or do you want a safe flyby and pure observation? And poll time, natural object, instrument, processing artifact, or artificial probe? Where do you place 3I Atlas right now? But pick carefully, because each choice predicts a different next observation. If it's natural, the stall should repeat with distant scaling, and deeper spectra should eventually tease out faint gas signatures or dust behavior. If it's processing, a new reduction pipeline should erase the stall instantly and leave a normal hyperbolic flyby. However, if it's artificial, the stall could correlate with attitude changes, meaning the light curve phase locks to the stop in a way rocks struggle to mimic. So what single measurement breaks the tie in one night? The team schedules the breaker. Simultaneous observations from widely spaced sites. One telescope starts around 2110 local in the west. Another starts 7 hours later in the east. And a third grabs the gap, because overlap matters more than total hours. They aim for at least 45 minutes of truly simultaneous frames. If parallax drives the stall, different sites should see the stall timing shift. But if the object drives it, every site should see the timing line up after correcting for light time. Only a few seconds of difference. However, the team needs one more thing: a spectrum during the stall. If the spectrum changes while the motion flattens, something turns on for 6 hours and then turns off. So what turns on? And then the last risk hits: losing the target. At about 2.4 AU, a small object can fade quickly, and a single cloudy night can inflate the uncertainty ellipse into tens of arc minutes, an ocean of stars where a dot can drown. But the network stacks exposures, 30 seconds each, hundreds per night, to keep the signal alive. Each stack buys another chance to see whether the 6-hour stationary point repeats, vanishes, or mutates into something even harder to explain. Because here's the crazy part. Interstellar objects do not wait for us to get good at this. So the cliffhanger sits inside the next clean dataset. Either the same 6-hour stationary point reappears under different telescopes, different pipelines, different baselines, and the stop becomes a signature we can hunt. Or the stall evaporates and turns into the most viral misunderstanding in space tracking history, and the real lesson becomes scarier. Our instruments can fool us so convincingly that we almost rewrite physics for a glitch. However, either ending changes how we search for the next visitor, because the next interstellar dot will arrive fast, faint, and indifferent to human confusion. What do you think causes the 6-hour stop? Geometry, fragmentation, outgassing, radiation pressure, or something active? Drop your best theory below, and I'll pin the most convincing one. Subscribe for the next orbit update and the next spectrum drop, because the next data either kills the stop or makes it worse. Next week, the black hole that eats itself.